Okay, for generation, we have direct and indirect AM. Direct, we use a device known as balance modulator. For indirect, we use methods such as using nonlinear devices or full AM modulator. And for detection parts, we have also this direct and indirect classification. For direct, we use balance modulator again, and indirect, we use envelope detector. Okay, for balance modulator direct detection, all AM variants can be detected using this technique. But for indirect envelope detector, this technique can only detect full AM signal. Okay, this is why, because in last week's topic, we have seen how the information, our VMT, is only located at the envelope of full AM, but not other types of AM. That's why it can only be used to detect full AM. Okay, since we use a lot of this balance modulator, I'll just introduce a bit on what is balance modulator. So actually, it's an IC circuit. It consists of many components. So it is used to do some functions such as creating double sideband signal. So what does it mean here, creating double sideband signal? Is that the carrier will be suppressed, so we have only the upper sideband and lower sideband. Okay, so that's the one of the main functions of balance modulator. And we have several types of balance modulators, such as this 1496 or 1596 IC and analog multiplier. And it's a very versatile device. Can use instead of producing single sideband signals, we can also use it for synchronous detection. So detection that use balance modulator is known as synchronous detection. Okay, but it can be complex and expensive. That's why we also teach about the indirect methods. They are less complex. But the detailed circuit inside balance modulator is not within the scope of our course. Yeah. Okay, so let's look at the first generation of full AM using direct method, using balance modulator. Okay, we start with this general equation of full AM. So it's EC plus VMT cos omega CT, right? So you can see here, if we expand, we have two parts, the EC cos omega CT and VM T cos omega CT. So here for our circuit, in this block diagram, how it can be generated, we can first, we have our carrier signal, this cos omega CT, and then using balance modulator, it will be multiplied with our VMT, message signal. And from this balance modulator, we have the output of VMT cos omega CT. So we know that when we have this kind of equation, VMT cos omega CT, we will produce double sideband signals without carrier, right? From the last lecture. So we'll produce FC plus FM or FC minus FM. Okay, for the below arm, here we multiply our carrier, so that is amplitude is EC. So this EC cos omega CT, then we sum with VMT cos omega CT. Then we got this first line here, EC cos omega CT plus VMT cos omega CT. So at the output of our mixer here, our summer here, we got our full AM signal, okay, which is EC plus VMT cos omega CT. So this is the direct using balance modulator. Okay, any question? No? Okay, I'll move to the next slide. Okay, so another method is using nonlinear device. Yeah, so this device is like diode, transistor. So what will happen is that both VMT and VCT will become input to our nonlinear device. And this nonlinear device normally it has its own function, yeah, like square law function. So here our input is VMT plus VCT. So our VMT is EM cos omega MT and VCT is EC cos omega CT. So the output of our nonlinear device, for example, here is VK, and what VK will do when it receive VI is that VI it will let it to follow this function. So output from nonlinear device will be E0, which is just DC, plus M1 VI plus M2 VI square, and so on. Okay, so this is what it will do to our V input. The rest are constants. Yeah. Okay, so we will just substitute our VI equal to EM cos omega MT and EC cos omega CT inside this equation. So we have E0 plus M1 VI and M2 VI square. So then we square. So we take only up to square. Yeah. So, and then we just expand. We got E0 plus M1 EM cos omega MT plus M1 EC cos omega CT plus, and then here when we square it becomes EM square cos omega M square, and then M2 EC square cos square omega C, and 2 M2 EM EC cos omega MT cos omega CT. Okay. So if you look carefully at the third line here, yeah, we have the DC component, the FM component, FC component, FM square, FC square, and then we have also the FC plus FM and FC minus FM. So from all these components, we ignore the like the cube and so on because they produce higher frequencies that we can ignore. So here we have all these components, yeah, at different frequencies. So if we want our full AM, what we can do is just we put filter. If you look at the diagram here, we put after nonlinear device a band pass filter, and this band pass filter we tune it at FC. Our resonance frequency is FC, and the bandwidth is plus minus FM. So when we set our frequency to be centered at FC and bandwidth FC plus minus FM, then it will accept only the carrier and the two sidebands. The rest of the components, this low frequency here in front and the high frequency here will be removed from our output. Okay, so this is like example of our output from the above equation. So if we rearrange, like we take the EC out, M1 EC, then becomes 1 plus 2 M2 over M1 EM cos omega MT times cos omega CT. So here we have, we can notice that there are similarities with our original full AM signal. Okay, so this is, and this one on top is the one that we have learned last week, and this is the one that is output from our nonlinear device. So we can see that instead of EC it became M1 EC. So this M1, M2, they are actually constants, not modulation index. So, and here 2M2 instead of M cos omega S, okay, this one here, M omega S is also same as omega M. Okay. So instead of just M cos omega S is 2M2 over M1 ES cos omega S. So we can see that the difference mainly at the amplitudes of EC and also amplitudes of EC and EM. Okay. But the frequency components are similar. Okay. So these are the frequency components before bandpass filter. But if we set our frequency response to be centered around FC, then after bandpass filter, only these three components will remain. So this is how we generate full AM signal using non-linear device, with the help of bandpass filter, of course. Okay, so far any question? No? Am I going too fast? Can you follow?
May I know how the 2M2 over M1 comes from?
Okay, this 2M2 of M1, actually it comes from this VK, the function of our nonlinear device. Yeah, it has just DC. First is not this one is just DC. And then we have VI, with is we can call it like multiplication factor. You know, this is the multiplication factor, a constant for VI. This M2 is the factor for VI square, M3 VI cube, and so on. So when we do this calculation, that is how we have our M1 and M2 inside our full AM equations. It's actually from here. We don't have to consider the one higher than square, because there are even higher harmonics that we can ignore, because we will tune our PF at FC anyway, and they will be removed. Okay, good question.
So that means the equation is derived from the previous one.
Sorry, can you say loudly?
So that means, right, the shock equation is 2M2 over M derivation from the VK, right?
Derivation from the, okay, yeah, it's actually from VK, you're right. We have to, the output of your V out depends, the V out here depends on this VK function. And normally this VK will be given. What are the functions of your nonlinear device? And then you just put your VI, and then you expand. After that, I think we have this kind of question in tutorial, right? If you notice. So it depends on your VK, right? The function of our nonlinear device. But the exact function will be given in the question. But normally it will be something like this lah. You have given like multiplication factor for the V input. Okay. So that is direct and indirect. Yeah, if you notice, direct one is normally very straightforward. Okay. Next is generation of double sideband suppressed carrier. So for double sideband suppressed carrier, that you just use balance modulator. And this is even just very straightforward. because the function of this multiplier is also belongs to it's also a type of balance modulator. So since we know that balance modulator produce double sideband signals, so we can just use a balance modulator, and the output is our double sideband signals. Okay, so input again the same lah, carrier, and also our information signal VMT. Okay, so in the slides you will notice that the symbols for your information signal, and sometimes we use VMT, sometimes VST, so it's like, but VMT or VST, they all belong to the same signal lah, is the information signal. So this is our message, and then our carrier, and this is the output of our DSB signal. Yeah. So instead of constant amplitudes here, you can see that the amplitudes of our carrier follow amplitudes of our original or message signal. Okay, so in its analysis, if you look at the analysis, because here and before this we use just sign, right, sign signal to represent our carrier. So this one you emulate the pulse modulation. So here is the pulse carrier. So but our information is analog, so the carrier signal, instead of just sine or cosine omega c, because it's a square wave, we include the higher harmonics here until the third harmonics. So again, K is the multiplier sensitivity factor. Okay, so the output is K times VMT and VCT. Okay, so here K we just leave as it is, K, and then VMT, then our VCT. Yeah, in here we use the Fourier series that described above. Okay, but we just ignore again the this higher harmonics, because anyway it has when we have high harmonics, the amplitude will be much less. Okay, so we just concentrate on the fundamental frequency at omega c. Okay, so again it will produce the same signal, double sideband signal, fc plus minus fm. It's just the amplitude that will be different, and also here we have phase, because we use sine, so that's why we have the phase difference. But again, the frequency component is just the same, fc plus minus fm. It's just amplitude and here phase. Okay, so for indirect method with double sideband suppressed carrier, the indirect method we use two full AM modulators. Yeah, so the input signal is the same, but one of them will be inverted and different polarity. Okay, so the first input signal, half this VST or VMT multiplied with our full AM modulator, then we have our full AM signal, and then the one below, our carrier is multiplied with this inverted VST, then we'll produce EC minus VST times our cos omega CT. Okay, And then the top one above with plus, and then below apply minus. And then when we add these two together, these two signals together, yeah, the EC components will be removed, and then we have only the VNT cos omega CT term. Yeah, so here we produce our double sideband suppressed carrier signals, yeah, using 2 full AM modulators, but one of them is inverted. Yeah, and then our mixer here, the top one plus, below one minus. So that's how we use double sideband, produce double sideband suppressed carrier using indirect method. Okay. Next is the generation of single sideband suppressed carrier. Okay. For direct method, as again, is very straightforward. Since our single sideband takes either one, either lower or upper sideband, what we can do is put a band pass filter after our double sideband suppressed carrier. Okay. So this is the first part. The earlier part here is for generation of double sideband suppressed carrier, and then we send this signal to a band pass filter. So the single sideband filter will then produce single sideband suppressed carrier signal. Okay. So it's either you have to set the filter, so that it's either low sideband or upper sideband that will pass through. But the band pass filter need to be very selective, because this one, the bandwidth is even narrower than this double sideband signal. Okay. So for the generation of single sideband, okay, this is another method of generating single sideband using 2 balance modulator. Okay, these 2 balance modulator will produce signals, 2 double sideband signal with 180-degree phase difference. Okay, and this is the phase shifting circuit. So on top we have this one is our message signal. Okay, and then we apply 90-degree phase shift, so it becomes sine. So here our carrier, cos omega CT, we also apply 90-degree phase shift, so it becomes sine omega CT. So the one on top, output from our balance modulator, is EM cos omega MT cos omega CT, and the one below is EM sin omega MT sin omega CT. Okay. So, and then we mix these two, then we produce single sideband suppressed carrier signals. Okay. So this is known as phase shifting circuit, because we have introduced phase shift to our both information and also carrier signals. Okay, so let's look at how we can produce single sideband from mathematical analysis. So this is output from the first and the top balance modulator, and then from the second balance modulator is our signal, which is in sine. Okay, so remember, we mix these two signals together. Okay, so we have this EM cos omega MT cos omega CT and EM sin omega MT sin omega CT. So we expand it using trigonometry identity. Okay, so cancel. So this, when we mix it together, the upper sideband here will be cancelled. Okay, so and only left with the lower sideband. Okay, so this is phase shifting, yeah, so that we don't need to use band pass filter. Okay. As for the vestigial sideband, okay, for vestigial sideband, it's almost the same, like full AM or double sideband suppressed carrier. Okay, we use valence modulator, we generate. Okay, once we generate our double sideband signal, we then send it to a vestigial filter, and then this vestigial filter will filter out part of one of the sidebands, and then we have only the vestigial signal after the filter. Okay, so those are descriptions for generations of different types of AM signal. Okay. So next we have part for demodulation. Okay, but before that, do you have any questions or anything that you want to ask? Okay, we have one question here. Doctor, do we need to derive the equations in exam? And if so, how do you determine which term to take and filter out? In past questions, final exam question, yeah, there were occasions where this type of questions were asked. So actually, if you understand, it's not that hard. So to determine which terms to take and filter will depend on the question needs. If the question wants you to generate this type of signal, then you know that, okay, for this double sideband signal, you need to have bandpass filter tuned at FC, and then you have to make sure that it also cover FC plus minus FM. If it's single sideband, so your bandpass filter is only the up to bandwidth is only FM, not 2 FM.
Doctor,
Yeah.
Can you how to say like for the not the double, I think the first modulation technique you introduced
Put M.
Yeah.
Yeah.
The one where the indirect one.
Okay.
In this case, yeah, can you go back to the equations?
Okay.
How do you determine that these are the how to say, the curves, the amplitudes that you want?
Why the final answer just choose the one in the bracket one? Why ignore the others?
This one.
Yeah.
Okay, the one in red boxes. I mean, because we tune our bandpass filter at FC, and okay, here are all the. If you look at this, sorry, if you look at the output here, okay, we have DC component. This one F equal to 0, right? And then we have this one. Just focus on the cos, and this one cos omega M, cos omega C. So this one we have FM, right? The frequency. And then this FC, this one you have 2 FM, 2 FC, right? And then this one FC plus FM, FC minus FM. Okay, so these are the frequency components that we have. So at the band pass filter, at the output of our VK here, the output, yeah. So these are the mathematics equation, and this is the spectrum. So at the spectrum, these are all the outputs from VK. We have at our f equal to 0, amplitude E0, and then we have our at S or FM here, amplitude is M1 EM, okay, and so on. But when we tune our band pass filter at FC, okay, we tune at FC and then we let the bandwidth become 2 FM, so that the minimum frequency is FC minus FM and the maximum FC plus FM. So only these 3 components will be processed, will remain for the subsequent, for the subsequent stage. Like here, after band pass filter, the band pass filter will let only the FC, these 3 components, FC, FC plus FM, and FC minus FM. That's why the rest of the others, we just remove lah. And only these 3 components remain.
Doctor, what about the cos square omega CT term? On the most this term, the most right hand side. Yeah.
Yeah, this is 2 FM, 2 FC. These are the higher frequencies.
So doctor means that we only take the one inside the half hemisphere lah. Means inside the band pass filter. The outer one we all ignore it lah.
Yes, because outer one they won't pass. They will not be passed. Only these 3 will pass to the output.
So this one is fixed one means if we face the question, then we straight away just use the three things inside, the FC plus FS and FC minus FS.
Yeah, so that after band pass filter, okay, this is like your output before band pass filter. So after band pass filter, only these 3 will remain. Here you see output of the band pass filter, V out. You have the FC, FC plus, FC minus FM. Okay. After BPF, DC components filtered out. Yes. Because if it's a low pass filter, okay, I cannot show using my pen because I know something's wrong with this. And when I connect, suddenly my laptop shut down. So let me just, if it's a low pass filter, a low pass filter will take, a low pass filter will take, let me see if I can, that doesn't work. With, normally with low pass filter, we have the cut-off frequency. It's known as cut-off frequency. Okay, let me try. I hope it won't shut my laptop. Okay, low pass filter is like, okay, low pass filter, we have a term known as the cut-off frequency. Okay, so it's like this. This is 0 and this is your F. So this is the cut-off frequency of your cut-off frequency. So it will take frequency from 0 until the this cutoff frequency, low pass filter. Okay, only this part will pass. But a band pass filter is like this. You have this one center or tune frequency, your center frequency. So this is your bandwidth of your low pass band pass filter. Sorry, band pass filter. So for band pass filter, this part will pass. Okay, so the DC component frequency 0 is here at f equal to 0. So it will not pass a band pass filter. Band pass filter only allow FC plus minus it's half of the bandwidth. Okay, if this is your bandwidth, so it's your bandwidth is this FC minus FM. This one is FC plus FM, right? So bandwidth is 2 FM. So only this part will be passed from our band pass filter. Okay. I'm glad that it doesn't shut down my laptop. Okay, so that's why if you look here, I know it's quite, it looks complicated the equation, but if you focus just on the one that is passed by the band pass filter, then you can only take the 3 components. The rest just ignore. Okay. Wait. Okay, any more questions? I don't think I have time to go for demodulation today. So we continue this Wednesday for demodulation part. Okay, any more question? Oh my God.
So doctor, how we choose this when we're going to use the SSB, SCN, or this DSBSC is based on the question lah.
Yes.
Means the question will state which equation we are going to use, right?
Yeah. But sometimes it's not that direct lah. Depends on the wording. But you can guess like it's a full AM, it's a double sideband suppressed carrier, it's a single sideband, but vestigial never comes out, but all just these 3 double sideband, full carrier, with carrier, without carrier, and single sideband. Okay, so hopefully this Wednesday I'll give you some kind of summary from direct to indirect, the step that you need to carry out, so that it becomes direct, become indirect, and to differentiate different AM variants. Okay, any more question? Okay, so if there's no question, I'll stop here. And then we'll continue next week with new topic, which is demodulation and also super heterodyne. Yeah, hopefully we'll be able to, I think we're supposed to finish AM this week. Yeah, then followed by FM. After that, 3rd of December, you have your test, second test. Right. Sorry, not second test, first
may
test.
I ask, test 1 is 3rd of December?
Yes, 3rd of December, 5:30 PM.
The syllabus until
FM.
FM. Okay.
So introduction, AM, FM, and AM. All these 3 chapters. and but it's higher lah in terms of percentage. It's 20%. Okay. So if there's nothing else, we stop here. And thank you very much for your attention. And see you this Wednesday, inshallah. But I have online conference actually on the same at the same time Wednesday. So I'll think about maybe I'll think of how to deal with it. Okay, thank you very much.